This is high gain boost converter with fuzzy logic controller. Here the input voltage it varies from 24 volt to 30 volt. Initially it was 24 volt. After 0.0 seconds it is increased to 26. After 0.125 second it is increased to 28. After 0.16 second it is increased to 30 volt. Similarly, here in this the load resistance is changed. Initially it was around 600 ohms. Here that R1 is 600 ohms. After 0.1 second, another resistance is connected. This is of 250 ohms. So the load is changed here. And also similarly, source voltage is changed. So how the fuzzy logic controller adapting those changes and provide load voltage regulation. Here the simulation is running now. Here this converter consists of two switches. Both will be turned on at the same time, and two inductors plus two capacitors. Okay, that is to provide boosted voltage. That is, it is to increase the voltage conversion ratio. And this output capacitance, it is to reduce the voltage ripples. If there is any oscillations present in the voltage, that will be reduced using this output capacitance. This is the input voltage, input current, and input power. Input voltage varying from 24 to 30. Here for input current, you can zoom it and check it. Initially it was 10 ohms, and after 1.1 second it is changed to nearly 20 or 22 ohms, 22 amps. So the input power is also changed here. And here this is the load voltage and current. Here the reference voltage it is around 400 volt. Here if you see means the reference we have provided as 400. That is compared with the higher DC load voltage, and error is converted into per unit, and that per unit error voltage is given to fuzzy logic control, and the output is the duty ratio. That duty ratio will be compared with high frequency carrier waveform to generate PWM pulses. So based on the error voltage, the fuzzy logic control will change the duty ratio. And this is the pulses generated from the PWM and provided to the switches. Here if you see in this waveform, this is the error voltage and duty ratio. Whenever the error voltage increases, the duty ratio will increase and provide the regulation, load voltage regulation. And this is output voltage and current. Initially, the current is around 0.7 or 65 amps. After 0.1 second, when the load is increased, it is increased to 1.6 amps. Here the voltage remains same. It is around 400 volt. Here if you see this waveform, the settling time is around nearly 0.2 millisecond. Similarly, the peak overshoot is very less. Here, the peak overshoot will increase up to 4.1 volt, 4.1, 0.7 or 6 volt. And here, this is the voltage ripples. It is around 399.8 6 to 400 volt. So nearly point 0.6, 0.4 volt we are getting as the voltage ripples. So using the fuzzy logic controller, the settling time is less, and here the functioning time is more and more less, because during emergency it will act through the battery. And this is the efficiency and output power curves. The efficiency is around 90 percentage we are getting. So here if you see means using fuzzy logic controller, the sample time is reduced, the peak overshoot is very less, and settling time is very less, and also that voltage ripples are very less. Steady state error is also very less. The difference between the reference voltage and the measured voltage is the steady state error. Here if you see means it is around 400 volt. After 0.1 second it is reduced to 397 volt. So 3 volt difference is there. Again after 0.16 second it is increased to 400 volt, because due to the increase in voltage, input voltage. So it is not exceeding 400 volt. And the error is around, maximum error is around 3 volt, which is nothing but less than 1 percentage. So this is the working of that high gain boost converter with fuzzy logic controller. Here we have changing the input voltage also, and load also we are changing. And despite these changes, the fuzzy logic controller ensures the load will be get regulated. Load voltage will be regulated.